Today I'm going to teach you about improper integrals. If you haven't done so already, please go to my website and print out these notes so you can follow along. An improper integral is calculating an area of a region that is not bounded. So it can be not bounded in two ways. It can be infinite in the x direction, where this goes off to the right forever, or infinite in the y direction, where this goes up forever. The x direction is called type 1, and if it's infinite in the y direction, it's called type 2. And these are done in slightly different ways. And the question is, do they have infinite area? And sometimes they do, and sometimes they don't. The key idea is that improper integrals are calculated using limits. And two vocabulary words here. If the limit is finite, we say that the integral converges, and if the limit is infinite or does not exist, we say that the integral diverges. So converges and diverges, two very important vocabulary words. Let's talk about each of the two types. Type 1 is an improper integral with an infinite limit of integration. So look at the picture. This one goes from x equals 0 to x equals infinity. So how do you compute an integral from a to infinity? What you do is you take the integral from a to b, some finite number b, and then you push b to infinity in the limit. So let's do an example here. Calculate the area under y equals e to the negative x in the first quadrant. Now to do these problems, you really have to draw the picture. It's very hard to do these correctly if you don't draw the picture. So this is what y equals e to the negative x looks like. And if you didn't remember that, you have to review your pre-calculus graphing skills so that you can draw pictures for these to make sure that you write out the integrals correctly and the limits correctly. So we want this area. So what is that? That is from x equals 0 to x equals infinity of e to the negative x. And we see that the correct way to compute this is to do the integral from 0 to b, where b is some number here, and then push the b all the way along the x-axis towards infinity. So we compute this integral, we'll get an expression in terms of b, and then at the last step we actually do the limit. So let's do it in this case. The antiderivative of e to the negative x is negative e to the negative x, and we evaluate that from x equals 0 to x equals b. So we get negative e to the negative b, and then we plug in a 0. E to the 0 is 1, so we get minus negative 1, so it's plus 1. Now we take the limit, because we now have an expression with b and there's nothing else to do with this expression in brackets. Now we take the limit as b goes to infinity. And as b goes to infinity, e to a very large negative number goes to 0. This piece goes to 0. So in the limit, this just becomes 0 plus 1, which is 1. And that's our answer. So this is a case where we have this unbounded region that goes off to infinity, but it actually has a finite area. It's part of the beauty of calculus. Okay, let's do another example. Number 2, calculate the area from negative infinity to infinity of, this is 1 over 1 plus x squared dx. So we're looking at the curve y equals 1 over 1 plus x squared. And if you think about it for a minute, it looks like this. And you want the area from x is infinity to x is negative infinity. So all of this. Again, this could be an infinite area or it might be a finite area. So one word of caution, it might be tempting to write out the limit like this, to say the limit as b goes to infinity from negative b to b of whatever the integrand is. So that we would take a negative b and a positive b and push both towards infinity at the same time. Unfortunately, you cannot do it that way, so do not do that. That's something different called the Cauchy principal value, and it's beyond the scope of this course. So sometimes this would work, but sometimes it wouldn't work. So don't do it this way. The correct way to do an improper integral where it's improper at both ends, like it goes off to negative infinity and positive infinity, the correct way is to break it up into two pieces. Let's say from negative infinity to 0, so the left half here of dx over 1 plus x squared, plus the integral from 0 to positive infinity. That would be the right half. This will work. So let's now write out limits for each one. Let's do the first one. I'm going to write the limit as b goes to negative infinity of the integral from b to 0. You could also write as b goes to positive infinity and then make that a negative b. It's your choice. Plus, and you can write out a similar expression for this, like the limit as b goes to infinity, 0 to b, dx over 1 plus x squared. Now, let's just focus on this one, because by symmetry, you can see that whatever this half is, the other half is going to be the same thing. So let's just do one of them. Actually, let's just do the right one, because there's no negative signs floating around. So this one is the antiderivative here is the inverse tangent. And if you didn't remember that, you have to memorize that. This is one of those special integrals. The antiderivative of 1 over 1 plus x squared is arctangent. So we get whatever this one is, plus the limit as b goes to infinity of tan inverse b minus inverse tangent of 0. Well, the inverse tangent of 0 is 0. So then we have to think about what this is. Well, the inverse tangent of infinity is asking you what angle would give you a tangent that is very large, near infinity. And if you think about drawing a triangle, a right triangle, where the tangent, the ratio of opposite to adjacent, is big, you need a big opposite side and a small adjacent side in order for that ratio to be big. So this angle, you can see, needs to be as close to 90 degrees as possible. In the limit, therefore, the inverse tangent of infinity is 90 degrees, or pi over 2. So this thing is pi over 2. Now, you could actually work out this other one, but by symmetry, it's also pi over 2. And so the answer is pi over 2 plus pi over 2 is pi. And that's the area here. Let's do another example. Let's now switch to type 2 improper integrals and do another example. So a type 2 improper integral, if you look back at the first page, it involves a vertical asymptote, like this one, where the y, it becomes infinite in the y direction. So improper integrals involving vertical asymptotes are defined with one-sided limits, such as this one. So the area from A to B is the area from A to C, and then you push C towards B from the left in this case, or maybe from the right, depending on the picture. You have to draw the picture for these in order to make it clear how to correctly write out the limit. So let's do an example. calculate the area under y equals 1 over square root of x from x equals 0 to 1. So we draw the picture. Y equals 1 over square root of x looks like this, and we're going from 0 to 1. So we want this region. Now you can see from the picture that the issue is at 0, not at 1. In other words, the endpoint that makes this an improper integral is the 0, not the 1. The 0 is where it goes to infinity. So the integral we want, which is this, can be written as, the limit of the area from b to 1 as we push b towards 0 from the right. Now we just have to do this antiderivative. Now to do this antiderivative, if you didn't have this one memorized, the trick with radicals sometimes is to write them as fractional exponents or negative exponents or whatever, and then use the power rule. So add 1 to the exponent to get positive 1/2, and divide by that positive 1/2 to get the antiderivative. So we'd have x to the 1/2 divided by 1/2, which is x to the 1/2 times 2. So it's 2 square root x, evaluated from b to 1. Now, what is that? That's 2 radical 1, that's 2, minus 2 radical b. Now that we have an expression with just b in it, and we're done with the integral part, we now take the limit and push b towards 0. In that case, 2 radical b, when b is 0, becomes 0. So we just get 2 minus 0, and the answer is 2. So again here we have a finite area here. Let's do an example where we won't get a finite area. Investigate this thing. Let's draw the picture. Notice the interval goes from 0 to 2, but in the middle there, at x equals 1, this function is not defined. It would be 1 divided by 0. So there's actually going to be a vertical asymptote here at 1, and if you think about which way the graph moves around the vertical asymptote, it's going to move sort of up on the left and down on the right. And again, if you're not sure about that, it might be helpful to review your graphing skills. So we want this area here. And looking at the picture, it looks like whatever this area is going to cancel whatever this negative area is here. So we get 0. But it's not 0 if this is infinite and this is infinite. In that case, the area is undefined, and we would say the integral diverges. So it's important to do the integral to actually see if it converges or not just assume it's going to be 0. So how do we do this? Well, from the picture we see we have to split this up into 2 pieces. The area from 0 to 1, and then the area from 1 to 2, because there's this discontinuity at 1. So let's do the left one. For this region here, from 0 to 1, the endpoint that makes the integral improper is at 1, not at 0. So we're going to take the area from 0 to b and then push b towards 1. push b towards 1 from the left. For the other one, the issue is at 1 again, not at 2. 1 is what makes the integral improper. So we're going to take the area from b to 2 and then push b back towards 1 from the right. Excuse me, limit. The area from b to 2 and push b towards 1 from the right. So this is the correct way to set up this improper integral. Now, let's just work on one of these two integrals, because you can see again from the picture that they're going to be the same, but one is the opposite of the other. Let's just do the first one, and we'll see what happens. So the antiderivative here is the negative natural log of absolute value 1 minus x. The negative sign is to undo the chain rule that results from the negative in front of the x. If you couldn't do that in your head, it's fine to do a u substitution or something on the side. But this is how it turns out. And let's see, what happens here? Well, we get the limit as b goes to 1 from the left of the negative natural log 1 minus b, and then when you plug in the 0, you get natural log of 1, which is 0. So adding or subtracting 0 doesn't change this, so you just get this. Now what happens? Well, when you push b towards 1 from the right, 1 minus a number slightly smaller than 1 will be a very small positive number. And if you think about the natural log of a very small positive number, like 0.00001, it's a very, very large negative number. If you're not sure about that, think of the graph of natural log of x. So this goes towards negative infinity. So we have negative infinity, which is positive infinity. So this whole limit is infinity. Plus, it doesn't matter what happens here, and in fact this one would be a negative infinity. But when you have an infinity as part of your limit, you can just say the integral diverges and you're done. So again, we don't consider infinity plus negative infinity to be 0. We say that diverges. Infinity minus infinity in math is an indeterminate form, like 0 divided by 0. Okay, let's just very quickly skim one more example here. So the only difference between this example and the previous one is that there's a power of 2/3 in the exponent. So what happens? Well, we're going to have the same, almost the same setup as this. A limit as b approaches 1 from the left of 0 to b. Let's see, 1 over 1 minus x to the 2/3 dx. And when you do this integral carefully, it's not going to be a natural log. And you'll have to take my word for it or do it yourself to confirm that it comes out to be 3. And then the other side of it, the area from b to 2 in the limit also becomes 3. So you end up with 3 plus 3, which is 6. My only point in skimming this example is to show you that this looks very similar to this, except there's a power of x in the denominator, and it changes the answer drastically from infinite to finite, from diverges to converges. So I want to use this as a segue to talk about how powers of x in the denominator can matter a lot in terms of convergence and divergence. So on the next page here, I put the tip you need to know about this, which is that y equals 1 over x is a sort of boundary function between convergence and divergence. And this chart, that some people call the p-test, tells you what happens to improper integrals of these two different types, the type 1 and type 2, for the very common function 1 over x to a power. And it turns out it's entirely governed by the p. If the power is greater than 1 or less than 1 or equal to 1, it converges or diverges or whatever. So I've laid it out in this little chart, but just to help you interpret it, here's what it means. Look at this first row. The area from 1 to infinity of things like 1 over x squared, 1 over x cubed, 1 over x to the 10th, 1 over x to any power that's bigger than 1, all of these converge, all of them. And that's this C in the box indicating that if you have the area from 1 to infinity of 1 over x to the p, and p is greater than 1, it always converges. This can of course be proven, but I'm not going to do that. You can look it up in your textbook or in any textbook or on the internet for a proof of why this is true. Let's look at this example. What about the area from 1 to infinity of 1 over x to a power that's less than 1? 1/2, 1/5, -6, 0.999. All of these diverge. Now, so the boundary is 1 over x to the 1 itself. If 0.99 diverges and 1.001 converges, then the number 1 itself is the boundary. So where does it belong? It turns out that 1 over x to the 1 dx, 1 over x dx belongs in the diverges category. It belongs on that list. Now, what about the other version, the type 2 version, where instead of going off to infinity on the right, we are concerned about the vertical asymptote of these functions at x equals 0? Well, then the exact reverse happens. The x squareds, x cubes, x to the 10th, x to the 1.001, these all diverge, and the exponents that are less than 1 converge in that case. And again, the 1 over x itself belongs on the diverge list. And that's summarized in the table at the top of the page. But this is a really useful tip to know when you're guessing whether functions converge or diverge. Integrals converge or diverge, rather. One more thing to point out here. When you determine whether or not an improper integral converges, only the tail matters, namely the improper end. So, for example, in all of these, I could change this 1 to a 7, and it would not change convergence, because the thing that governs convergence is the infinity or not. That's what makes the integral improper, so that's what governs whether it converges or not. Where exactly you start, at 1 or at 7, only adds or subtracts a finite amount of area under the curve. So it's not going to make infinity not infinity, and it's not going to make something that's not infinity into infinity by adding a small finite area, like the area from 1 to 7. So you can change the endpoint that's not the improper one and not change whether or not it converges. Although you will of course change the actual area itself if it does converge. So you can do the same thing for these integrals where 0 is the issue, the 1 over 0 situation when x is 0. So you can't change the 0, but you could change the 1, like you could change it to an 8, and it would still diverge. It doesn't matter if you change the end that's not the tail. And the word tail just comes from the fact that improper integrals look like they have this tail either here or here. One more small thing to mention is that scaling and shifting does not, these functions does not change convergence or divergence. So for example, if I changed this 1 to a 2, I'm just simply doubling the area So I'm not going to change whether or not it converges. I'm just going to change the finite number to a different finite number. So you can multiply, you could shift things, like for example, you could replace in a lot of cases, although you have to be careful, let's replace this x in the x to the 10th by, replace it by x minus a half. And I believe, so I replace it by x minus a half to the 10th instead of x to the 10th. I believe that would not change the actual value or the convergence of the integral or not, as long as you didn't create any other issues with where the endpoints are. So just be aware of that kind of stuff. Let's talk about the direct comparison test. If we can't evaluate an improper integral directly, we might still be able to determine whether or not it converges. So here's the direct comparison test. It says if you have two functions, f and g, that are both positive, and g is always bigger than f, then if the integral of g converges, then so does f, and if the integral of f diverges, then so does g. Now this may seem a little bizarre until you draw the picture, in which case it should make sense. So here's the picture. Here's your function g, and then here's a function f below it, and they're both positive. And this is saying that if the area under g converges, so all of this, if all of that is finite, or sorry, it doesn't have an endpoint here, that's the whole point. If the area under g converges, then so does f. Well, that's clear from the picture. If all of this area is finite, then the smaller area under here is obviously also finite. It's just a smaller finite positive number. The second line says the same thing, but in reverse, really. If f of x diverges, so if the small area is infinite, if it diverges, then of course the larger area under g is also infinite. It's somehow more infinite. It diverges too. So just think of it as something bigger than infinity is still infinity, and something smaller than a finite number is still finite. So how do we apply this test? Let's do this example. Show that the integral of sine squared x over x squared converges by comparing it to the integral of 1 over x squared. So according to the comparison test, to show something converges, we need to find something larger than it which also converges. And then this will be a smaller number, and so it will also converge. So let's think about why we can replace sine squared x with just 1. Well, sine squared x is always less than 1, because sine is between -1 and 1. So let's write it up like this. Since sine squared x is less than 1, we can divide both sides by the positive number x squared to say that sine squared x over x squared, this function, is smaller than this function, 1 over x squared. And notice both are positive numbers. So, we know that this thing, the simpler version, 1 over x squared, converges by the p-test. If you look on the previous page, when we talked about the p-test, this integral converges because of the 2 in the exponent. So, replacing the 1 with the sine squared just makes it smaller. So whatever this number is, we don't even care what it is. This is smaller and still positive, so it must also converge. That's it. So again, to prove something converges, look for something simpler and slightly larger that also converges. And to prove something diverges, look for something simpler and slightly smaller that diverges. This is not the only time in doing improper integrals problems that you might want to replace something complicated like sine x with something simpler like 1. Go to the next page, and I'm going to give you the last little topic here, which is a time-saving tip for deciding convergence or divergence. My tip is to figure out which endpoints of the integral are the ones that make the integral improper, and then use some kind of approximation to come up with an initial guess of whether or not the integral converges. Now, what do I mean by approximation? I mean things like near x equals infinity, the function 1 over x behaves like 0. So we can replace 1 over x with 0. Or here's every professor's favorite, near x equals 0, the function y equals sine x behaves like the function y equals x. So you can replace awkward instances of sine x with just x if the improperness comes from a 0 at an endpoint. Let me give you an example here of how to use this kind of thinking. Suppose you're taking the exam and you flip to the last page, you have 2 minutes left, and you see this question, which one of these 3 integrals converges? And you think, there's no way I could possibly do 3 integrals in 2 minutes, I'm just going to have to run out of time and get this wrong. Well, that's not true. I think we can do this problem in 2 minutes. So let's try it. Which one converges? We look at the first one, cosine x divided by x, and we look at the limits, 0 and 1. The thing that makes the integral improper is the 0, not the 1. The 0 would give you a 0 in the denominator when x is 0. So what's going on at 0? Well, near x equals 0, cosine x behaves like the function 1. So we can say it behaves as if it were 1 over x dx. That means approximately, or behaves like. And by the p-test, this thing diverges. So it's not that one. Let's look at this next one. X plus x squared over x to the 4th with a square root. Which endpoint makes the integral improper? It's the infinity, not the 1. The infinity is the issue. So near infinity, which is more important, x or x squared? Well, x squared is much bigger than x near infinity. So you can forget the x. That's not the important part. And you can approximate this as the square root of x squared over x to the 4th, which is the square root of 1 over x squared, which is 1 over x again. Also by the p-test, this version of the 1 over x improper integral also diverges. So it's not that one. Therefore, it must be this third one that converges. Let's just confirm that by looking at this integral. Again, the infinity end is the improper one. And near infinity, x squared is much bigger than x. So forget about x. This is now the square root of x squared over x to the 5th, which is the square root of 1 over x cubed, which is 1 over x to the 3 halves. That says 3 halves as a fraction. And now you think about the p-test. You're looking from 1 to infinity, and this p, this exponent, 3 halves, is bigger than 1. So by the p-test, this converges. And you're done. Hopefully that took us about 2 minutes. All right. If you understood all this, you're now ready to do it yourself. I would suggest you computing these 3 improper integrals yourself, and also deciding if these integrals converge or diverge. All of these 4. My hint for the 4th one is to use the comparison test and compare to e to the negative x, and draw the picture of both. After you've done all that, you are ready to do the homework.